Hi, my name is Calvin Schnell and this is my Lab 4 report on oscillation and energy. In this video, I'll walk through how I modeled a mass spring system in VPython, compared it to the real tracker data, and tested whether energy was conserved. I'll also show how calculated oscillation period in both x and y directions and what those results mean. The purpose of this lab was to connect theory with experiment. I wanted to see whether the computational model based on the physics principles matched the motion measured in tracker, whether the total mechanical energy stayed the same, or whether the oscillation in x and y had the same period. System description. The system I modeled was a mass attached to a vertical spring. Gravity pulled the mass down and the spring pulled upwards according to Hooke's law, which when it stretched or compressed. The system included the mass and the spring, while the surroundings consist of earth, which provide gravity and an anchor point. The lab used two main physics principles, the momentum principle and the energy principle. I used the net force to update momentum and position step by step in VPython. Then at each step, I calculated kinetic energy, gravitational potential energy, spring potential energy, and checked whether the total of these consistently stayed the same. To analyze the real motion, I recorded a video and imported it into Tracker. I marked the mass frame by frame. The initial position was about negative 0.12 meters in the x and negative 0.612 meters in the y. The mass started from rest, and I exported this motion as a CSV file to use in my model. For my VPython model setup, in the simulation I entered the same initial conditions from the tracker with the mass of 0.402 kilograms and spring constant was 6.83 newtons per meter, and at the relaxed spring length of 0.123 meters. I calculated gravity downwards and spring force based on how far the spring was stretched from its rest length. Here's some of my code. My code imported it into the tracker data, plotted the real motion against the model, calculated the force, and used momentum principle to update the motion. It also computed all three energy types at every time step so I could check whether the total energy stayed constant. This is the model versus tracker on the x position versus the time. When I compared the x position of the mass over time, the blue curve showed the VPython, while the red points showed the measured data. The two match very well in frequency and motion pattern, but there are slight phase shifts over time which are likely due to damping or experimental inaccuracies. Here is the motion versus tracker in the y position. In the y direction, the model also follows the tracker data closely. The model keeps the consistent amplitude because it assumes no energy loss, while the real motion slowly decreases in amplitude due to the damping force like air resistance and internal friction. Here is my energy plots. I examined how the energy changed over time. I plotted the change in kinetic energy, gravitational potential, spring potential, and total energy. Each type of energy stays as the mass moves, but what matters is whether the total stays the same. The total mechanical energy stayed almost perfectly constant throughout the simulation, while only tiny fluctuations due to numerical roundings. This means the energy principle is satisfied, and the only noticeable change happens right at the start when the energy begins with the stored spring and gravitational energy, not zero energy. From the x position in the tracker, I measured the time between the two peaks of motion. The oscillation period in the x direction was about 0.18 seconds. This is consistent over several cycles. Using the y position graph, the period was slightly shorter, about 1.55 seconds. The difference between the two periods suggests that the motion was not perfectly one-dimensional. Some of the energy shifted between the vertical and horizontal motion, and the real-life damping affects the tracker data more than the model. There were several sources of error in the tracker. Marking each point manually can introduce pixel-level inaccuracies. Air resistance and internal friction weren't included in the model, and the spring might not have been perfectly vertical. The camera angle could also distort the measurements slightly. In conclusion, my computational model successfully matched the motion from tracker in both x and y directions. The energy principle was satisfied because the total mechanical energy stayed constant during the simulation. The oscillation period in the x and y were similar but not identical, mainly due to the two-dimensional motion and real-world damping. Overall, the experiment and the model agreed well with each other. Thank you.